I'd like to welcome you all to this webinar, LiDAR applications for pavement projects. I really appreciate you taking the time out of your day. I know everybody's busy to tune into this webinar, and I hope the information I present to you is informative and well received. So first off, I know most people tuning in are relatively familiar with mobile LiDAR. So my goal here today is to just dig a little deeper and showcase the benefits of utilizing mobile LiDAR on pavement projects. So let's go ahead and move on to some bookkeeping items. As stated previously and in the advertisement, this presentation is about LiDAR applications relating to pavement projects. We're going to talk a little bit about all of the different facets of a pavement project and how mobile LiDAR can contribute to and be beneficial in those aspects. We're going to talk a little bit about planning, asset management, how mobile LiDAR can be utilized for mapping support on engineering design projects, the benefits of it with regard to earthwork quantification on both the estimating side from an engineering standpoint, and also for compliance analysis and verification after construction. All right, so first off, before we really get into the meat of the subject, I think it's really important to spend some time discussing the accuracy and repeatability of mobile LiDAR. Excuse me, sorry, I'm getting a phone call there. I don't know if you can hear that. Just let me get back to what I was saying. So anyways, Clay Wygant, who is my boss and mentor with regard to mobile LiDAR mapping, has always told me the first thing you got to do is prove the solution. And once you prove the solution, you, as well as the end user, can have confidence in the analysis and the mapping products that are derived from that data set. So I want to spend a little bit of time talking about how we prove the solution and just to give you that sense of confidence and trust in the quality data that we can produce from a mobile LiDAR data set. So basically here you see on this slide, basically talks about the accuracy. That's all dependent on the project control and also the project needs. Some projects require higher levels of accuracy. Pavement projects being one of those. We really need precise information with regard to cross slope analysis and things like that. The system is, mobile. We can collect design grade information at all the way up to highway speeds, complying with posted speed limits so that we're not hampering traffic or having to shut down roadways and things like that to be able to capture the data. It's a safer collection process. We're keeping surveyors out of the way. I am a licensed surveyor and I started my career, boots on the ground out there doing conventional field collection and things like that. So I understand the dangers that are involved with that. And anytime we can keep people out of harm's way, that's always a plus. The utilization, there's a multitude of applications for mobile LiDAR. What's listed there: corridor mapping, topography, analysis of structures, utilities, asset management, planning, things like that. And another one of the big benefits related to our collection is that we are collecting 360-degree high-resolution imagery. And that's very beneficial because it just basically captures an accurate snapshot of what the existing conditions were on the ground at the time that the scan was performed. It's also very beneficial for other users down the process in the design process to be able to go back and look at what the site looks like with high resolution imagery, the ability to zoom in and out. It basically is like a Google Earth-like experience, except with high resolution imagery. The other benefit to that is you can actually extract individual images from that 360 spherical imagery for planning purposes, for meetings, things like that. So it's just a very useful tool, and it has been well received by most of our clients. So basically, to prove the solution, as I said earlier, what we want to do is you want to show that any type of measurement technique that you're utilizing is repeatable. That's one of the most critical aspects of measurement, is that it's repeatable. If it's not repeatable, then it's not dependable. And if things aren't dependable, people can't rely upon them. So, the level of precision for mobile LiDAR, can vary. It's basically dependent on the project as stated previously. It can, for mapping grade projects like GIS, asset management projects and things like that, typically plus or minus a foot accuracy is probably sufficient. Mobile LiDAR is more than capable of meeting those standards and requirements, and that's right out of the box. There's a couple different ways mobile LiDAR is utilized. We can actually just scan a roadway and then process a trajectory against a GNSS base station, and that basically geo-references our positions. And the quality of that data, unless we're in severe GPS obstructed environments, will 99% of the time meet mapping grade standards. For design grade, we actually implement survey control, which is similar to any other type of remote sensing like photogrammetry or anything like that. We actually have surveyors go out and set targets along the roadway at given intervals, usually about 1,000 feet per target, depending on the accuracy requirements. If the accuracy requirements are a little bit less, we can spread out that target spacing and cut down a little bit on the cost on the effort for the ground survey control. But aside from that, that's kind of our standard when we're really trying to achieve high level design grade mapping, which would be about 1,000 foot target spacing. Surveyors would go out there, measure those targets, provide us coordinates, and then we take that information along with the mobile LiDAR data collection that is done and basically adjust the LiDAR data set so that it coincides with that survey control. So, and basically to give a little example here of how we prove the repeatability, we've done some studies on our own where we scanned the same roadway corridor multiple times at different times of the day under different conditions, because we basically want to accommodate and account for all of the different variables that can come into play when we're doing a mobile LiDAR collection. We felt that this was important to be able to show that regardless of the conditions that we're operating in, the system has a level of precision that is repeatable and trustworthy. One thing I would point out is not all LiDAR systems are created equal. We use Regal mobile LiDAR scanners. We have two systems. We have the VMX-1HA, which is a dual sensor system, and also the VMX-450, which we've had upgraded, and it actually incorporates the same IMU that's in the VMX-1HA. So we call it the VMX-450 Plus. Speaking to that, there's different types of mobile LiDAR systems out there. And, one of the most critical components of a mobile LiDAR system is the IMU, the inertial measurement unit. And basically that controls or limits the quality of the data that can be produced. So there's some systems out there that are meant more for asset grade and things like that. And basically the quality of the IMU solution is a little bit less in that it won't allow you to achieve these design grade accuracy requirements for pavement projects and the like. Okay, so here, this has some statistics or some analysis and information on the 3 tests that we ran. Like I specified, we scanned the same corridor 3 different times at 3 different times of the day. What you see on the left side of your screen is basically the deltas to survey control targets that were set for the 3 different scan projects. And what I'd like to point out here is that you see a level of consistency and precision, which shows the repeatability of the system, even without any control. You see those deviations there from the control point that shows up in the mobile LiDAR data to the actual surveyed value. And they range anywhere from 1/10 of a foot up to 3/10 of a foot. Again, this is all dependent on the GPS environment. We've actually done some other work in areas where there's very minimal GPS obstructions. And with an uncontrolled data set, we've been able to match into survey control and conventionally collected survey data via GPS, RTK, and robotic total station measurements within 1/10 to 1500ths, which is very impressive without it introducing any control into the solution. So there in the middle, you see after adjustment. So this is basically showing you, um, you know, where those targets showed up in the mobile LiDAR data set after being adjusted to the survey control, which if the survey is, excuse me, if the software is working properly, the values should look like they are there. Now, one thing I always say is the true test of the quality of your data is not how well you can adjust to the survey control, because that's more of a software routine and the software should be able to do its job. The real test is, what does your data look like in areas where you're not adjusting to control or you don't have any survey control available? And this is something that we really pride ourselves on. We've done numerous types of tests. We worked with several different sub-consultants that provide survey control for us on on projects we do throughout the country, where they'll collect survey data in between or away from our control points, cross sections, or for example, in Florida, FDOT has standards where they require verification targets, which basically results in a blind QC of the data set. So and we've thoroughly tested our methods and our approaches, and we've documented that we can achieve accuracies up in the range of about 600s per foot at the 95% confidence interval. You see there the blind QC checks there. Those are basically just points that we measured away from scan target control via RTK GPS. We had the RTK GPS measuring relative to the same base station that was used for the mobile LiDAR trajectory processing. And there you see the results. They vary anywhere from, less than 100th up to right at 600ths of a foot. So, that just, and we show that across 3 different data sets, 3 different times, 3 different days, that we're able to achieve that repeatability and that consistency. And it basically establishes the level of precision of the data that we can produce. Okay, on this screen, you see there, this is basically some standard accuracy reporting that we do on projects. This is for compliance with FDOT standards. I'm going to zoom in a little bit here so you can see this report, because it's a little hard to read more than likely on your screens. But basically what this is these are the validation targets that I referenced, or verification targets, excuse me. And those are basically set in between the scan control targets. So if we have scan control targets based at 1,000 foot intervals, there'll be a verification target that's placed at 500 foot intervals away from the scan target control. So basically you see here, this project had about 20 verification points. This spreadsheet just documents the deviations from the measured point in the LiDAR data set to the actual survey control values. There you see the deltas for the X, Y, and Z, and then also the NSSDA statistics. And if I get that, I always get that acronym wrong, but it's the National Standard for Spatial Accuracy. And those are kind of standard statistics, which I'm sure most people are familiar with on how to judge the quality of geospatial data. Here on the side, you see basically it's just a little bit of a blow up of, excuse me, let me see if I go back. Showing basically the accuracy statistics from an NSSDA standpoint. You see there that the RMSE values in the X, Y, and Z, the highest value there is 2.5 hundredths in the X. You also see the statistical analysis at the 95% confidence level. So from a horizontal standpoint, we can say that this data set is accurate to 5.5 hundredths horizontally at the 95% confidence interval, and 2.5 hundredths vertically from a vertical standpoint. And the reason we were able to achieve those levels of vertical accuracy is we actually ran digital levels through all of the survey control and the verification targets on this project. So that's one way that we can really tighten up our vertical on a project and ensure that when you're pulling an elevation out from a data set, that it's going to match the project datum and the project control, within these type of tolerances. Okay, now I think we've basically proved the solution. So I think the next step is we want to move on to some of the applications of mobile LiDAR for pavement projects. First one I want to talk about is pavement condition analysis. As most people are probably aware, this is something that most DOTs do throughout the nation, and many municipalities also. What's kind of standard throughout the industry is the Pavement Condition Index, the PCI. What you see here on your screen is just some analysis that we've run on a LiDAR data set, which basically shows some rutting that's evident in this two-lane road. It's color-coded there based on the severity of the rutting, the yellow being more severe. We can basically generate these reports according with the ASTM standards, or if individual agencies and municipalities have their own standards, we can modify our tools to accommodate for those and generate these type of raster images and subsequent reports in compliance with those standards. Here on this next screen, you see basically some of the different features that can be detected when doing this pavement condition analysis. And then also just some of the benefits of utilizing LiDAR for this analysis. Basically, LiDAR removes the subjectivity because in the past, this was always done by human observers out in the field. It also allows us to do a full analysis of the entire roadway versus just doing samples and then doing interpolation between that to make a determination of the quality of the road surface. Another benefit is everything is automatically geo-referenced, and we can also take this information into multiple formats. We can put it in a shapefile format for consumption in a GIS environment. We generate these raster images, which are very user-friendly and easy to interpret. They're color-coded based off of the severity of the depressions. We can also generate custom reports in terms of volumes of depressions and things like that. So that would be a nice tool that somebody could utilize if they're going to send a crew out to go, fill in potholes and things like that. You can basically come up with some precise quantity estimates on how much materials you're going to need to rehabilitate a given area. The next thing we'll talk about is the roadway cross slope analysis. This is a project that we did in Florida also for a client, basically where they wanted to get a quick and efficient way to analyze the existing cross slopes of a road that was a mill and inlay was going to be performed on. And that's basically key because most projects, unless they're a profile milling project, it's mill a certain depth and then put it back. But if the existing conditions are out of the specified tolerances for cross slopes, that can be an issue. So this is a very beneficial tool that allows you to quickly identify cross slope deficiencies and also can help you analyze the profile of the roadway and identify deficiencies in that also before you actually get on the ground and start doing any work. This can be done both from an uncontrolled data set, which would really just provide relative analysis in terms of a cross slope percent, or if the data set is controlled to survey controlled, then we can pull elevations out of that data set from these resultant cross slope analysis and basically provide survey grade elevations. All right, next I want to talk about basically utilizing mobile LiDAR for mapping support for engineering design. Mobile LiDAR is a very beneficial tool for generating very accurate and detailed surface models that accurately reflect the existing conditions of the pavement surface. I like to refer to them as high density tin surface models. And the reason I refer to that is because we're sampling the mobile LiDAR point cloud at very high frequencies so that anytime an end user is pulling an elevation from a tin surface, more than likely you're very close to an actual measurement that was taken from the point cloud, and you're not having interpolation over 25 or 50 or 100 feet, which is usually the norm for other mapping sources like conventional cross sections collected on the ground at 25-foot intervals, or aerial mapping where usually break lines are collected at anywhere from 25 to 50 to 100-foot intervals between nodes on the break lines. So basically it just increases the ability of the tin surface to accurately model what the actual roadway surface looks like. Okay, this screen just gives you a little bit more information on how we generate those high density tin surfaces. The top shows basically a cross-section profile we use this methodology called key point extraction, which basically we're allowed to set a tolerance on this tool, and it will basically kind of trace along the profile of the roadway at that cross section, and it'll pick up all the undulations in the pavement, which there's really not any other measurement technique that's geo-referenced that allows you to do something like this in a quick and an efficient manner. On the bottom there, to the left, you see basically those cross sections from a plan view. One other thing we do is, the two lines on the outside are the edge of pavement. This is a 2-lane road, actually Interstate 40 here in New Mexico. Just to make the triangulation really clean, we ensure that the nodes on the edge of pavement break lines line up with the cross sections so that the triangulation just comes across very cleanly, and all the triangulation is longitudinal and transverse to the road to get the best representation of the road surface. Another benefit to this is we can do this extraction and mapping on project stationing if that is already developed, which can also be beneficial because then when an engineer is generating cross-section profiles for their design, they're actually looking at measurements that were taken directly from the point cloud versus an interpolated area. The bottom right picture there just shows a cross-section in Civil 3D that's generated from an alignment from the tin surface that was generated from the mobile LiDAR, and it just shows that the cross-section accurately reflects those breaks or grade breaks in the cross-section profile. Okay, this screen is basically just an analysis of the quality of the tin to be able to model the mobile LiDAR point cloud. We've proved that the mobile LiDAR point cloud is an accurate reflection of the conditions on the ground. The top screen, or the top image there, shows the mobile LiDAR tin surface and running this analysis of basically the mesh of the tin surface to the point cloud. If you see the scale on the left side, it anywhere ranges from 0 up to 1500ths, and you can see that throughout the entire data set, we're in the range of green. So basically our tin surface is within 300ths or less of what the actual mobile LiDAR point cloud elevation values are. And on the bottom there, you see an aerial tin surface that was generated for this same area. And basically, this was a project where we mapped the hard surfaces with mobile LiDAR, and then we contracted with an aerial firm to do photogrammetry to map the areas outside of the mobile LiDAR limits, because obviously mobile LiDAR has limits in terms of how far out you can map from where the scan vehicle is. So, we do this a lot. We create these hybrid mapping data sets so that you get the best of both worlds. You get the full coverage you need for, drainage analysis and things like that, but you also get a very high detailed and accurate surface for the roadway surface. And, this isn't in an attempt to, badmouth or say anything bad about photogrammetry. I think this just shows that you need to choose the right tool for the job. Not every tool is the proper tool to be utilized for that job. And just one other point I want to make, if you look at the bottom, the scale for the aerial photogrammetry is in the range of 0 to 4/10. So it shows that there's a lot more variance between the point cloud and the tin surface generated from the aerial mapping. Okay, now I just want to talk a little bit about how we deliver. One thing we pride ourselves on is making our data consumable to the end user. So we can basically put our data in any type of format that the end user is comfortable working in, anywhere from a GIS environment to traditional CAD environments. All the different CAD providers out there, we're comfortable and experienced in producing data sets that can go into those formats. Another thing we like to talk about is the ability to utilize web portals. What you see here on your screen is Topo Cloud Pro, which is one of the web portals that we utilize. We also use several others, another one being Pointera, and we're flexible. If a client has a specific web portal that they've been using, we can definitely work out a way to get our data into those formats. What you see here is basically an interface which allows you to look at the project limits of what was mapped. This interface allows for the LiDAR data to be downloaded if necessary. We can also have the vector information in there, like the line work that was extracted for brake lines, curb lines, things like that in here. And one very key interesting feature, which I'd like to point out in the bottom right-hand screen, this is the high resolution imagery that we collect. The user has the ability to interface with this and take measurements in this web-based platform, which doesn't require any special software. It's very intuitive. Anybody can use it. You don't have to be checking out licenses or make sure you're connected to the network to be able to access your network licenses for CAD software, things like that. So basically it allows anybody from, a project manager up to, a program manager, all the way down to a technician, anybody to be able to get in here and do some quick analysis. You can measure cross slopes, you can measure heights, a lot of things that would otherwise require you to get into a CAD environment or do a site visit, even just to look at something and see what it looks like. You can do this and really save a lot of time. It can also be very beneficial for planning meetings, things like that, to be able to allow everybody at once to be able to look at this information, be able to discuss it and have it right in front of you. Okay, so I think that basically covers what I wanted to cover today in this webinar. Just give a little recap. We proved the solution on the quality of the mobile LiDAR data set. So that shows that the end user can have the confidence in the data that's derived from the mobile LiDAR data. Talked a little bit about how the mobile LiDAR can be utilized for planning and asset management, which is related to pavement condition analysis. We talked about how we can support the design process with very accurate, high-density DTM models. Earthwork quantification, one thing I really didn't get a lot of chance to talk about, but we have some experience where we've been able to do some comparison in terms of volume comparisons between a photogrammetry-derived surface and a mobile LiDAR-derived surface just within the roadway footprint or the hard surface area. And one project that comes to mind for me in particular, it was about a 2-mile long project. And over that 2-mile long project, doing a volume, tin to tin comparison, we saw a difference of almost 10,000 cubic yards between the mobile LiDAR data set and or the tin surface and the aerial DTM tin surface. So again, it's always important to remember you need to use the right tool for the job, and especially in pavement projects where cross slopes and profiles and things like that are very critical. I believe mobile LiDAR is the best tool for the job. One other thing, compliance after construction. This is another tool, and we're about to be starting a project like this down in Florida, where we're actually going to scan and then do some processing to ensure that the roadway was constructed properly and the cross slopes conform with the project specifications. Okay, just first off, I just want to say thank everybody for tuning into this webinar, and now I'd like to open it up for question and answers.
Great, thank you very much, Jacobo. We have a couple questions here. The first one is from Dan. Can mobile LiDAR be used for profile milling?
Yes, it can. That's a very good question, Dan. Like I said, I mentioned a little bit, I didn't cover it very much, but we have done some projects that are profile milling projects, and that's basically to correct the profile longitudinally of the road. Mobile LiDAR is a very beneficial tool to perform analysis on the existing profile of the road and use that as the basis for developing the corrections necessary to correct the profile of the road to meet project specifications.
Thank you. Another question from Joe. How precise is a lane cross slope computed from LiDAR?
Okay, another good question. Like I said, that's more of a relative analysis, and because of the way mobile LiDAR works, and it's operating so fast, we're basically utilizing light pulses. So the speed of light is a benefit to us in this type of analysis, because the objects that are remotely sensed across a lane are sensed within a microsecond, or a fraction of a second. So the relative precision between those two measurements from one side of the lane stripe to the other is probably at the level of differential leveling in terms of the relative elevation difference between one lane stripe to the other. So we can achieve cross slope accuracies that are accurate to 0.1% accuracy.
Okay, thank you. A question from Shannon. How does LiDAR compare to other mapping technologies from a cost perspective?
That's another good question. And, I think we've proved the quality of the data. So, like the old adage goes, you get what you pay for. But that being said, we understand that we, as mapping providers, need to operate within the space and, with the budgets that are out there. So, we have developed very streamlined workflows and processes that allow us to be cost competitive with any other type of mapping source, with the understanding that sometimes a level of detail and accuracy is required and really not achievable from any other type of measurement source. So, in those instances, it can be a little bit more costly, but in the end, it can also be very beneficial because it can introduce a lot of cost savings on the back end in terms of quantity estimates, quality of the data, the ability to have confidence before people get out in the field on the project to start working that you're not going to run into unforeseen problems.
Okay, thank you. That actually will wrap up the questions that I have from the audience here. So let me just check. Yep. No other questions came in. Do you want to have any last remarks or comments, Jacobo, before we end the WebEx?
Sure. First off, I just want to thank you, Maria, for assisting with the moderating, and I want to thank everybody that tuned in today. I really appreciate you taking time out of your day. I know everybody's busy, and anybody that has any questions, you see contact information there. The survey webinars at majorconsulting.com. Please feel free to reach out if you have any projects that you think we can assist you with. We'd be more than happy to talk about that with you and do our best to assist you with that. Thank you.